Welcome back to the deep dive. Today, we're really digging into a major shift, maybe the major shift, in AI development right now. How do we efficiently build real autonomous agency?
Yeah, exactly. We're not just talking about making chatbots slightly better at chatting anymore.
No, this is different. It's about moving from AI that mostly thinks, reasons, writes text to AI that actually works.
Agents that can take on tasks, use tools, get things done in the real world or, well, complex digital worlds. It's a big leap.
And the research we're looking at today, it gives a really solid definition for this idea of agency. They call it an emergent capacity.
Right, emergent. It's not something you explicitly program line by line. It's about the system learning to be autonomous.
Discovering problems on its own, coming up with ideas, testing them out, using tools, all self-directed.
Think about the difference. An AI assistant suggests some code to fix a bug versus an AI developer actually figures out the bug, writes the code, tests it, and submits the pull request. That's the goal.
That's a huge difference. And there's a lot of pressure to get there, right? From thinking AI to working AI.
Immense pressure. But the standard playbook, based on language models, has always been scale, 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 more data, bigger models.
The old scaling laws. More complexity needs more data. Simple as that, or so we thought.
Exactly. And that's where this paper, LIMI Less is More for Intelligent Agency, just throws a wrench in the works.
A big wrench. It challenges that whole idea.
It really does. It introduces what they effectively call the agency efficiency principle. And the core finding is, well, it's pretty stark.
Go on.
Machine autonomy, the kind you need for real agency, doesn't just bubble up from having mountains of data. It comes from being really smart, really strategic, about curating high-quality examples of agentic behavior.
So, quality over quantity, but taken to an extreme.
An absolute extreme. It's about the richness of the interaction, the complexity of the problem-solving trajectory, not just the number of data points.
Okay, when I first read the abstract, I have to admit, I was skeptical. How can you just bypass scaling laws like that? So, our mission today is to really get into the technical details, the methodology, the evidence they present.
And we absolutely have to start with the headline result because it sets the stage for everything else.
Right. LMI, using this curated approach, scored 73.5% on Agency Bench. That's the big benchmark for this stuff.
Which is already impressive because it blows past the baseline, a very capable GLM 4.5 model, which only got 45.1%.
But here's the kicker, the part that makes you sit up and pay attention.
Yeah.
LMI did this with just 78 training samples.
78. Let that sink in. We're comparing that 73.5% score against models that were fine-tuned on, 10,000 samples?
Exactly. It's a 53.7% improvement using 128 times fewer samples.
I mean, that's not just an incremental gain. That's potentially an inflection point, right? It changes the economics, the architecture.
Yeah.
It shifts focus from just raw compute power to, let's say, instructional design for AI.
Okay, so to really grasp this, we need to start where the paper starts. Defining agency properly and looking at these complex tasks. That's section 1.
Right. Let's chart the path. We started with LLMs that were mostly passive assistants, right? Good at generating text based on prompts. Think back to the early big models.
Responding to input, basically.
Yeah. But now the push is towards proactive agents. Systems that don't just respond, but act. They need to handle tasks on their own.
Which means they need a whole different set of skills, not just language.
Definitely. They need autonomous task execution, doing things without step-by-step guidance. They need serious multi-step reasoning, keeping track of a goal over many interactions.
And they need to work with humans and tools, right? Collaborative problem solving, integrating feedback, using APIs, handling errors.
It's about taking a high-level goal, breaking it down, using tools, dealing with things going wrong, and explaining what's happening. Much more complex.
And traditionally, the assumption was for that kind of complexity.
You needed massive data. That's what the Kaplan scaling law suggested. More complexity, more data. Big models followed that path.
But we have seen some hints that maybe this isn't always true even before LIMI, like LIMI for alignment.
Exactly. LIMI showed you could get good alignment with just 1,000 really well-chosen examples. The signal was dense.
And then LIMO did something similar for math reasoning, right? Again, relatively few, very strategic samples.
Right. So the question becomes, why is agency different? Why might complex agentic behavior need less data than, say, mastering raw language fluency or simpler reasoning?
And the paper argues.
The paper argues it's because agency is about learning the protocol of problem solving. It's about interaction, planning, tool use, error recovery. Pouring in tons of low-quality static data just adds noise. What you need are high-fidelity examples of the entire strategic workflow. That's the catalyst.
Okay, so to test that, you need tasks that really push this agentic capability, long horizon tasks.
Precisely. These are the multi-step challenges that demand sustained effort. The paper breaks down 4 key demands these tasks place on an agent.
What are they?
First, temporal complexity. This is tough for LLMs. The agent has to track the state of things over many turns, sometimes dozens. It needs cumulative reasoning. It can't just react to the last input, it needs the whole history.
Makes sense. Keeping track of the plot. What's second?
Second, strategic planning. This means breaking down a big goal into smaller steps, and crucially, being able to change the plan if something unexpected happens, like an error message or weird feedback from a tool. That adaptive loop is key.
Like real problem solving. Third
is tool orchestration. Agents don't work in a vacuum. They need to use multiple tools together, maybe search for something, use that result on a code editor, run a test, parse the results. It has to be coordinated.
Okay. Integrating different systems seamlessly. And the last one?
Collaborative communication. Since these are often human-AI collaborative tasks, the agent needs to communicate effectively, explain its plan, report results clearly, ask good clarifying questions when it's stuck. It's not just a script, it's a collaborator.
Got it. Temporal complexity, strategic planning, tool orchestration, and collaborative communication.
And you can see all 4 of those come together beautifully in one of the key examples from Agency Bench, the Gomoku Battle Task. Task 3, it's a complex coding job. Build a web-based Gomoku game from the ground up.
Okay, walk us through that. How does it test agency?
Well, it starts relatively simple. Subtask 1 is just the basics. Build the front end, render a 15 by 15 board, handle players taking turns, basic HTML, CSS, JavaScript, test fundamental coding, and setup.
Okay, standard web dev stuff.
But then Subtask 2 ramps it up. Implement efficient win detection, O1 complexity, using incremental neighborhood checks, and highlight the winning line. Now you need algorithmic thinking and dynamic updates.
Getting trickier. What's next?
Subtask 3 is about state management. Add underrato, keep a move history, allow step-by-step replay. This hammers that temporal complexity point tracking and manipulating the game state accurately over time.
Right, managing the history. That can get messy.
Very. Then, subtask 4, you start adding AI opponents. Rule-based AI, maybe heuristic, like win if you can in one move or block the opponent's 4 in a row. The agent has to implement strategic logic now, not just game mechanics.
Okay, adding some intelligence. But the real challenge is...
Subtask 5. Advanced AI. Implement hard and expert levels using proper algorithms minimax with alpha-beta pruning. And for expert, you need things like fixed depth search, maybe 2 or 3 moves ahead, candidate pruning, and strict time limits like 500 milliseconds per move.
Wow. Okay, that's implementing a classic AI search algorithm with performance constraints. That requires deep planning, recursion, careful resource management.
Exactly. Learning to navigate that entire 5-step process, including dealing with errors and maybe asking for clarification along the way, that's the kind of high-quality, complex trajectory they curated for LIMI. It's not just one piece of code, it's the whole journey.
Which brings us right to section 2, the LIMI methodology. If scale isn't the answer, how did they actually design these 78 golden examples?
They were very focused. They didn't try to cover everything. They picked 2 key domains where agency provides massive value: vibe coding and research workflows.
Let's define those. Vibe coding. Yeah, that sounds like more than just writing code snippets.
It is. They define it as collaborative software development. The agent acts like a peer developer. It needs to understand existing code, navigate complex development environments, debug iteratively, and communicate technically with a human collaborator. Think pair programming, but with an AI.
Okay, so complex interactive coding and research workflows.
That covers the scientific process. Things like searching literature, analyzing complex data, designing experiments, even generating insights from results. It requires reasoning across different types of information and often using specialized scientific software or tools.
So 2 really high-value, complex knowledge work domains.
Precisely. And the foundation for training was how they formalized the data. It wasn't just input-output pairs. The basic unit is a tuple.
Query and trajectory.
Right. The query tuller is just the high-level goal in natural language. Build the Gomoku game, for example. But the magic, the signal, is in the trajectory.
Have a trajectory.
It's the entire sequence of actions needed to successfully complete the query. Every step, every interaction. That's where the 128x efficiency comes from, packing so much learning into that sequence.
And they break down the actions within the trajectory too, right, into specific types.
Yes. 3 crucial types. First, model reasoning. This actually captures the agent's internal thought process, its analysis, planning, decision-making steps. Training on this teaches the model how to approach the problem strategically.
So you're teaching it the meta skill of planning. Interesting. What's second?
Second, model tool calling. TUJ. This is the agent actually using a tool calling an API, running a command in a terminal. Training on this makes sure it learns the right syntax, the right parameters, how to interact with the environment correctly.
The practical execution part and the third type.
Third, and maybe most critical for agency, is environment observation. This is the feedback the agent gets, the results from a tool, a clarification from the user, or very importantly, error messages, stack traces, things going wrong.
So training on observations teaches it how to handle feedback and, crucially, how to recover from errors.
Exactly. It learns error parsing, diagnosis, correction strategies. It learns resilience. This whole formalization moves learning away from static examples to the dynamic process of interactive problem solving.
Okay, that makes sense why it might be so much more efficient. Now, how do they get the 78 initial queries? The $2, that seems like a tiny number to cover these complex domains.
It is tiny. They used a clever two-pronged approach. 60 of the 78 came from real-world collection. They literally got tasks from professional developers and researchers. Some research tasks were even based on the complex workflows described in actual academic papers, so high ecological validity.
Grounded in reality. What about the other 18?
Those came from an innovative process they called GitHub PR-based query synthesis. They used GPT-5, but in a very controlled way.
How so? Not just scraping random pull requests.
Definitely not. They set strict criteria. First, only repos with more than 10,000 GitHub stars, ensuring the projects were substantial and well-structured.
Load of control.
Then complexity filtering. They looked at pull requests, but focused on ones with code changes, diffs, under 1,200 tokens. This filtered out trivial changes, but kept ones complex enough to require real agentic problem solving. Substantive, but focused.
Okay, hitting that sweet spot of complexity.
And crucially, human oversight. 4 PhD students acted as expert annotators. They reviewed thousands of synthesized queries generated by this process, but only selected 18 that perfectly captured the core agentic challenges in vibe coding and research workflows, ensuring semantic fidelity and task complexity. It was extreme curation.
Wow, so thousands generated, only 18 selected to complement the 60 real-world ones. That's a serious focus on signal density.
Absolutely. Then, with the 78 queries defined, they needed to collect the trajectories, the TOWIE. This required a special environment.
Right, you need to log everything perfectly.
They use something called the SII-CLI environment. Apparently, it's very good for integrating lots of tools, allowing flexible human-AI collaboration, and most importantly, detailed logging of the entire interaction trajectory, essential for creating those rich TOWIE tuples.
And how did they actually generate the trajectories within this environment?
Again, the 4 PhD student annotators worked with GPT-5. They took each of the 78 queries and worked through them iteratively until the task was successfully completed.
So they captured the whole process, warts and all, the back and forth, the dead ends, the debugging.
Everything. The authentic communication, the error diagnosis, the steps taken to recover, the refinements, that's the gold.
And the resulting trajectories must have been pretty long and complex, even if there were only 78 of them.
Incredibly complex. The average trajectory length was over 42,000 tokens. The longest one hit 152,000 tokens.
Whoa.
So yeah, it's only 78 samples, but each sample is an epic problem-solving session, fully documented. The sheer token count per sample shows the depth of the signal being captured. It's teaching the whole multi-round protocol.
Okay, that paints a much clearer picture of why 78 samples could be so powerful. It's 78 incredibly dense learning experiences.
Exactly. So now that we understand the data, let's move to section 3, the experiments. How did they prove this efficiency actually translates to better performance?
Right, the validation. They needed strong baselines to compare against.
And they used them. We're talking state-of-the-art models here. GLM 4.5, which is a big 355 billion parameter model. Its smaller sibling, GLM 4.5 Air, the huge Kimi K2 Instruct, a 1 trillion parameter mixture of experts model, DeepSeek V3.1, Qwen 3, basically a representative slice of today's top-tier models.
The serious lineup. And how did they set up the comparison?
All the fine-tuning was done consistently using the same framework called SLIME. The key comparison was LIMI, which is the GLM 4.5 model fine-tuned on those 78 strategic samples versus the same GLM 4.5 architecture fine-tuned on much larger existing agentic datasets.
Datasets like?
Things like CC bench trajectories, the AFM web agent dataset, the AFM code agent dataset. Some of these have up to 10,000 samples.
So it's a direct face-off. 78 curated samples versus thousands of samples from broader agentic datasets. Quality versus quantity.
Precisely, the perfect test for the agency efficiency principle.
And the main battlefield was agency bench.
Yes, agency bench was the primary benchmark. It's specifically designed for these collaborative, long-horizon tasks. Remember the Gomoku game? That's one of the 10 tasks. Others include things like building a C++ chat system, a Java task manager, orchestrating microservices, complex research workflows, really demanding stuff.
And agency bench uses specific metrics, not just overall accuracy.
Right, and they're quite nuanced, all judged within a limit of 100-303 interaction rounds per query. First, there's first-turn functional completeness, FTFC.
What's that measure?
It's the percentage of the task requirements that the agent gets right in its very first response. High FTFC means good initial planning and understanding, less need for back-and-forth correction.
Okay, a measure of initial quality, then there's success rate.
Yep. Success rate,
Yeah.
SR at R, standard metric. Did the agent successfully complete the task within the 3 allowed rounds? Measures overall reliability.
And the third one, RC at R.
Remaining chances, RC at R. This measures efficiency. If the agent finishes successfully, how many of the 3 rounds did it have left over, on average? High RC at R means it not only succeeded, but did so quickly and efficiently.
Got it. FTFC for planning, SR for reliability, RC for efficiency. A much richer picture of agency.
Definitely. But they didn't stop there. They knew people would worry about overfitting with only 78 samples.
Naturally. So generalization testing was key.
Absolutely. They tested on a range of other benchmarks. Specialized tool use tasks like booking flights or retail scenarios, standard coding benchmarks like human evil and MBPP.
Plus domain-specific ones.
Yes, crucial for their focus areas. Data science benchmarks like DS1000 and scientific coding with SciCode.
And importantly, they tested with and without access to that SII, CLI environment, right?
Critical control. Testing without the CLI tools helps isolate how much of the improvement is genuine reasoning and planning ability versus just getting better at using the specific tools in that environment.
Okay, a really thorough setup.
Okay.
Designed to isolate the effect of the curated data.
Exactly. It sets the stage perfectly for the main results in Section 4, which really do validate this whole less is more idea.
Let's hear them. Agency bench first, the overall score.
LMI hits 73.5%. The best baseline, GLM 4.5, is way back at 45.1%. It's not even close.
And that FTFC metric, the first turn quality.
Huge difference there. LMI gets 71.7% FTFC. GLM 4.5 only manages 37.8%. That's a massive 33.9 percentage point gap.
Wow, so LIMI is much better at understanding the task and generating a good first attempt, less fumbling around.
Much better initial planning and execution. It suggests the curated trajectories really taught it how to structure its approach effectively right from the start.
And reliability. The success rate.
Also strong. LMI's SR at 3 is 74.6% compared to 47.4% for GLM 4.5. It's just more likely to successfully complete the task within the allotted interactions.
And these gains were consistent across the board.
Yeah.
FTFC, SR, RC.
Yes, the improvements were seen across all 3 agentic metrics. It wasn't just better at one thing, it was more competent, reliable, and efficient.
Okay, now for the data efficiency comparison, this is the core claim. LIMI with 78 samples versus the big data sets.
Right. Let's take the GLM 4.5 model fine-tuned on 10,000 coding agent samples. GLM 4.5 code. Its score was 47.8%. LIMI, with its 78 samples, got 73.5%.
That's the 53.7% improvement with 128 times less data we mentioned earlier. It's just stark.
It really is, and it wasn't a fluke with that one dataset comparison. LIMI also crushed GLM 4.5 web, trained on over 7,000 web agent samples, scored a 36.7%, and GLM 4.5 CC, trained on 260 samples, scored 29.2%.
So the conclusion seems unavoidable. The way the data captures the agentic process in those 78 trajectories is vastly more important than just having thousands of less focused examples.
That's the inescapable conclusion from the agency bench results. It's the curation, the density, the focus on the full trajectory.
But did this highly focused training make it brittle? Did it generalize?
That's the next crucial piece of evidence. On average, across all those diverse generalization benchmarks, tool use, coding, data science, LIMI, still came out on top. It averaged 57.2% compared to 43.0% for the base GLM 4.5.
So the learning trend transferred. It wasn't just memorizing the 78 tasks.
Exactly. It learned underlying principles of planning, tool use, and reasoning that applied more broadly.
Any specific highlights on generalization?
Yeah, it did really well on the standard coding benchmarks, which is reassuring. 92.1% on eval plus human eval, 82.3% on eval plus MBPP. So learning complex agency didn't hurt its core coding skills, it likely enhanced them.
And the data efficiency held up on generalization, too.
It did. Compared to that GLM 4.5 code model, 10K samples, 40.9% generalization average, LIMI 78 samples showed about a 40% relative improvement even on these unseen tasks. The efficiency gain is robust.
One more check. Did this method only work on the big GLM 4.5 model?
No, and that's important for practicality. They tested it on the smaller GLM 4.5 error model, 106B parameters. Its baseline score was pretty low, 17.0%. But fine-tuning it with the 78 LIMI samples, making LIMI error, boosted it significantly to 34.3%.
So the curation strategy itself works across different model sizes. It's tapping into something fundamental about learning agency.
That's the implication. The training paradigm seems robust and transferable.
Okay, so the headline results are strong. Superior performance, incredible data efficiency, good generalization, works on different models. Let's get into the nuances in Section 5. The big question: how much of this is the model getting smarter versus just getting better at using the specific SII-CLI tools?
Right, disentangling intrinsic ability from tool proficiency. That's where the tool-free evaluation comes in. They tested the models on the generalization tasks without letting them actually execute anything in the CLI environment, judging them purely on their plans and generated code.
And the result?
Even without the tools, LMI still outperformed the others. It scored 50.0% on average across the generalization benchmarks in this tool-free setting.
How does that compare?
Still better than the base GLM 4.5, 48.7%, and significantly better than strong external models like Kimi K2 Instruct, 40.3%.
So what does that tell us?
It tells us that the LIMI training genuinely improved the model's core, intrinsic, reasoning, and planning abilities. The strategic curation made the model fundamentally better at figuring out what to do, independent of actually doing it with those specific tools.
That's a key finding. It's not just learning API calls.
Not at all. But, interestingly, the tools do help it express that improved capability.
How so?
Well, remember, LIMI scored 57.2% on generalization with the CLI tools, but only 50.0% without them. That 7.2 percentage point difference shows a synergy. Meaning, the training improved both the fundamental thinking and the ability to effectively use tools in a coordinated way. The environment lets the smarter model fully leverage its capabilities. It learned the reasoning and the practical execution skills needed for collaboration.
That makes sense. Better thinking combined with better doing. To make this really concrete, let's look at those case studies from Agency Bench. They really highlight the practical difference. Start with vibe coding.
Okay, task 1. The C++ chat system. Complex state, tricky language. The base GLM 4.5 model just fell apart. It hit an error trying to fix the chat history display, subtask 3, and couldn't recover. Then it timed out on the next subtask. A classic cascade failure.
And what?
Sailed through, completed all the subtasks without hitting those kinds of unrecoverable walls. It showed the resilience that the base model lacked. It could debug and replan.
What about the Gamoku game, task 3, with the advanced AI?
Another clear contrast, the base GLM 4.5 struggled even with the basics, rendering the board, detecting winds. It needed a lot of human help just to get the foundation right. And then, predictably, it failed completely on the hard part, implementing the Minimax AI with pruning. It couldn't handle that level of algorithmic complexity and planning.
Whereas LIMI?
Having learned from trajectories that likely included similar complex algorithmic implementations, LIMI managed all the prerequisites smoothly and successfully tackled the advanced AI subtask. It demonstrated the necessary foresight and structural understanding.
It's the difference between getting stuck and seeing the whole path.
Exactly. It's not just slightly better code. It's a different level of planning competence.
And we see similar gaps in the research workflow tasks.
Absolutely. Task 8 was about finding a complex scientific function to fit data extremely precisely.
High precision math.
Right. The base GLM 4.5 model needed several rounds of back and forth with the human annotator to finally reach the target loss value around 1.1E6. LIMI achieved a loss value an order of magnitude better, around 67, on its very first try.
Wow. First shot, much better result.
Yeah.
That implies way better initial analysis and planning.
Huge difference in insight. Then Ask 9 involved complex reasoning about NBA player stats, requiring web searches and integrating information.
Okay, real-world knowledge integration.
Yeah. On one subtask about James Harden, the base model got confused, ran out of interaction attempts, and started citing irrelevant old players. Total failure mode.
And LIMI.
LIMI also made an initial mistake on that one, interestingly. But crucially, it only needed one clarification prompt from the human to correct itself and get the right answer. It demonstrated self-correction based on feedback, a key agentic skill.
Learning from interaction.
Precisely. And on another subtask about Kevin Durant, both models eventually got it right, but LIMI did it much more efficiently. Fewer reasoning steps, fewer tokens used, faster response time, better accuracy, and better efficiency.
And there was one more subtask where the base model failed.
Yes, on the final Clay Thompson query, the base model again exhausted all its interaction chances and failed. LIMI needed just one corrective prompt to succeed.
So the pattern is clear across these cases. LIMI isn't just incrementally better, it's more reliable, more efficient, better at planning, better at recovering from errors, better at using feedback. It behaves more like an autonomous agent.
That's the story the case studies tell. The strategic curation genuinely instilled those core agentic capabilities.
Okay, let's wrap up this deep dive. Time to synthesize the key takeaways from LIMI and this agency efficiency principle.
Absolutely. Takeaway number 1. The core principle holds water. Strategic curation of high-density, complete interaction trajectories is radically more effective for building agentic capabilities than simply scaling up data volume.
The 73.5% agency bench score, with 128x fewer samples, is the smoking gun for them.
Undeniably. Takeaway 2. The unit of training is critical. It's not about isolated input-output pairs. It's about the full trajectory TOWI capturing the entire dynamic process of reasoning, tool use, observation, and error recovery in relevant domains like vibe coding and research workflows.
Learning the process, not just the answer.
Exactly. And takeaway 3. This approach is robust. It works across different model sizes, it leads to better generalization, and it improves both intrinsic reasoning and the practical ability to use tools effectively in collaboration.
So stepping back, what's the big picture implication here for AI development?
Well, it strongly suggests that building highly capable agentic AI might be less about winning the race for the biggest data center and the most GPUs.
And more about
being incredibly smart in how we design the learning experiences. It shifts the bottleneck, potentially, from raw resources to pedagogical skill, the ability to define, formalize, and capture these incredibly rich, distilled examples of problem solving.
It becomes more about AI curriculum design than just data harvesting.
You could put it that way. The focus moves to identifying and representing the essence of agency.
Which leads us to the final provocative thought for you, the listener. If complex agency, this ability to plan, act, and collaborate over long tasks, can be effectively taught using just 78 hyper-curated examples, what's next?
Yeah, what other advanced AI capabilities might be amenable to this less is more approach? Could we see similar breakthroughs in areas like complex multimodal reasoning or maybe even meta-learning and rapid adaptation by focusing on distilling the core principles into a few perfect examples rather than drowning the models in data?
The journey towards more capable AI, maybe even AGI, might depend less on the sheer size of the informational haystack and much more on our ability to design the perfect information-dense needle. Something to think about.